Long-distance transmission lines act as massive capacitors under light loads. This physical phenomenon, known as the Ferranti effect, causes dangerous voltage spikes at the receiving end of the grid. To prevent cascading equipment failure, transmission operators rely on oil-filled inductors called shunt reactors. But grid expansion plans have decoupled from manufacturing capacity. Lead times for utility-scale shunt reactors have quadrupled since 2018, rising from 12 months to 48 months. The structural supply deficit is projected to reach 15.8% by 2027. This bottleneck directly threatens the commissioning of over 45,000 circuit kilometers of planned transmission lines. This bottleneck is driven by extreme material intensity. A single 765 kilovolt shunt reactor requires 78 metric tons of laser-scribed grain-oriented electrical steel and 32 metric tons of high-purity copper. The production of this specialized steel is highly consolidated. Fewer than 10 mills globally can produce the grades required to minimize core losses. Copper requirements also scale nonlinearly with voltage. A 765 kilovolt unit requires 540% more copper by weight than a standard 110 kilovolt unit. This high material footprint exposes grid infrastructure directly to base metal supply chain volatility. The systemic impact of the shortage is a direct limit on the energy transition. Global demand for reactive power compensation is projected to reach 96,000 megavoltamperes reactive by 2028. Manufacturing capacity is growing at just 5.7% annually. This leaves a projected deficit of 29,000 megavoltamperes reactive. To prevent overvoltage failures, operators must either curtail remote wind and solar generation or run transmission lines below thermal limits. This physical constraint mirrors the grid crises of the late 1960s, when rapid high-voltage deployment outpaced compensation equipment manufacturing. Today, the physical limits of heavy industry again dictate the speed of policy ambitions.